Let yourself settle into whatever comfort you've found, whether it's the softness of pillows or the weight of blankets, or simply the quiet stillness of this moment. There's nothing you need to do right now, nowhere you need to be, nothing you need to understand or remember. What we're going to explore together is something vast and gentle, a story about everything, about the whole universe and how it works, told slowly and without any rush at all. It's a story about what physicists call the theory of everything, though that name sounds grander than it needs to be. Really, it's just an idea, a hope, a dream that all the forces and particles and laws that govern reality might fit together into one beautiful unified picture. And we'll wander through this idea together, taking our time, letting thoughts drift and return like tide pools filling and emptying under a patient moon. The theory of everything is not something we have, not yet, not completely. It's something we're searching for, something physicists have been reaching toward for decades, maybe centuries if you count back far enough. It's the idea that beneath all the complexity of the universe, beneath galaxies and atoms and forces and fields, there might be one simple principle, one elegant structure, one fundamental truth from which everything else flows. And even though we haven't found it yet, the search itself is beautiful, and the pieces we've gathered along the way tell a remarkable story about how the universe is put together. So let's begin gently, at the surface of things, with the world as you experience it. You live in a universe of objects and motions, of light and shadow, of cause and effect. Things fall when you drop them. The sun rises and sets. Water flows downhill. For most of human history, these were simply the facts of existence, the way things were, requiring no deeper explanation than the evidence of the senses. But slowly, over thousands of years, people began to wonder whether there might be patterns beneath the surface, rules that could explain why things happen as they do. The ancient Greeks thought about this. Philosophers like Aristotle, who tried to categorize motion and matter, who asked what things were made of, what made them move and change. They didn't have experiments in the modern sense, didn't have mathematics precise enough to make predictions, but they had curiosity and reason, and they built the first frameworks for thinking about nature systematically. Their answers were often wrong, but their questions were right, and those questions echo down through the centuries to us. Then, much later, in the Renaissance and the centuries that followed, something changed. People like Galileo and Newton began to use mathematics, began to do careful experiments, began to measure and predict with precision. Newton especially saw something profound. The same force that makes an apple fall from a tree also keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. Gravity, he realized, is universal. It acts on everything, everywhere, according to a simple mathematical law. This was perhaps the first great unification in physics, the first hint that seemingly different phenomena might be aspects of one underlying principle. You don't need to follow every detail of this history. Just let it wash over you, a gentle current of human thought stretching across centuries. Newton's law of gravity worked beautifully for more than 200 years, predicting the motions of planets and comets, explaining tides and orbits. But it wasn't the end of the story. It was just the beginning. In the 19th century, another unification happened, this time involving electricity and magnetism. People had known about both for a long time. Magnets attracted iron. Lightning cracked across the sky. Amber rubbed with fur could pick up small objects through some mysterious force. These seemed like separate phenomena, different aspects of nature with no particular connection to each other. But then James Clerk Maxwell, working with mathematics and experiments done by others, showed that electricity and magnetism were intimately related, two aspects of a single electromagnetic force. Maxwell's equations, as they came to be called, described how electric and magnetic fields interact, how they create each other, how they propagate through space as waves. And these waves, Maxwell realized, travel at a particular speed, a speed that turned out to be exactly the speed of light. This meant that light itself was an electromagnetic wave, that the glow of a candle and the pull of a magnet were manifestations of the same underlying force. It was another beautiful unification, another step towards seeing the unity beneath nature's diversity. As you listen, you might notice your breathing, the gentle rise and fall, the rhythm that continues whether you think about it or not. There's a rhythm to this story too, a slow movement from complexity toward simplicity, from many forces toward few, from scattered facts toward unified understanding. And this rhythm has continued, century after century, as physicists have peeled back layer after layer of reality's structure. In the early 20th century, two revolutions transformed physics. One was relativity, Einstein's insight that space and time are not separate, absolute things but aspects of a single fabric, spacetime, that can bend and warp in the presence of matter and energy. The other was quantum mechanics, the discovery that at the smallest scales reality is probabilistic, that particles behave like waves, that measurement and observation play strange and fundamental roles in determining what happens. These two theories, relativity and quantum mechanics, are both extraordinarily successful. Relativity explains gravity as the curvature of spacetime, predicts black holes and gravitational waves, describes the expansion of the universe. Quantum mechanics explains atoms and molecules, chemical bonds and radioactive decay, the behavior of light and matter at scales too small to see. Together, they account for essentially everything we observe in the physical world. And yet, they don't fit together. They're mathematically incompatible in deep ways. Relativity is smooth and continuous, describing spacetime as a gentle fabric. Quantum mechanics is discrete and probabilistic, full of uncertainty and jumps. When you try to combine them to create a quantum theory of gravity, you run into problems, infinities, predictions that don't make sense. This is one of the great challenges in physics, perhaps the great challenge, finding a theory that unifies quantum mechanics and gravity, that works at all scales, from the smallest particles to the largest structures in the cosmos. This unified theory, if it exists, is what people mean when they talk about a theory of everything. It would be a framework that includes all the forces, all the particles, all the phenomena we know, and explains them as aspects of one coherent structure. It would tell us what spacetime is made of, why the forces have the strengths they do, why particles have the masses they have. It would be the deepest level of description we could reach, the fundamental code underlying reality. But let's not get ahead of ourselves. Let's slow down and think about what we already know, about the pieces we've already gathered, because they're beautiful in themselves, and understanding them helps us appreciate what a theory of everything would mean. The universe, as we currently understand it, is made of two basic kinds of things, matter and forces. Matter is the stuff things are made of, particles like electrons and quarks that combine to form atoms, molecules, all the tangible substance of the world. Forces are what make matter interact, what holds atoms together, what makes objects attract or repel, what governs how things change and move. We know of four fundamental forces. There's gravity, which pulls masses together, keeps planets in orbit, makes apples fall. There's electromagnetism, which governs electricity and magnetism and light, which holds atoms together and makes chemistry possible. And then there are two forces you don't encounter directly in everyday life, because they only act at very short ranges within atomic nuclei. One is called the strong nuclear force, which holds quarks together inside protons and neutrons, and binds protons and neutrons together in nuclei. The other is the weak nuclear force, which is responsible for certain kinds of radioactive decay, for processes that happen in the sun's core, for subtle transformations between particles, four forces. And the matter particles, the building blocks, come in several families. There are quarks, which come in 6 types, and leptons, which also come in 6 types and include electrons and neutrinos. And then there are force-carrying particles, like photons that carry the electromagnetic force and gluons that carry the strong force. All of this is described by what's called the Standard Model of particle physics, a quantum theory that works astonishingly well, that's been tested in countless experiments, that predicts the results of particle collider experiments with remarkable precision. The Standard Model is one of the great achievements of 20th century science, but it's not complete. It doesn't include gravity. It doesn't explain why the particles have the particular masses they do, why there are 3 generations of matter particles, why the forces have the strengths they have. It has many parameters, numbers that have to be put in by hand based on experimental measurements, rather than being predicted by the theory. And this suggests that there's something deeper, some more fundamental theory from which the Standard Model emerges as an approximation. You might feel yourself drifting, your mind wandering, and that's perfectly fine. There's no need to track every detail, to remember the names of particles or forces. Just rest in the sense that there's a structure here, a pattern, layers of understanding built up over generations of careful thought and experiment. We're moving slowly through this landscape, and you can drift with it however you like. Let's think about unification again, because it's central to the whole story. Maxwell unified electricity and magnetism. In the 1960s and 70s, physicists unified electromagnetism with the weak nuclear force, showing that they're two aspects of something called the electroweak force. At very high energies, the kind that existed in the early universe, these two forces become indistinguishable manifestations of a single underlying symmetry. As the universe cooled, this symmetry broke, and the forces separated into the distinct phenomena we see today. This was a profound insight, and it suggested a natural question. Could the strong force be unified with the electroweak force? Could all three non-gravitational forces be aspects of a single grand unified force? Many physicists think the answer is yes, and there are several proposed grand unified theories, though none have been confirmed experimentally. The unification would happen at even higher energies than the electroweak unification, energies so high we can't reach them in laboratories, energies that only existed in the first tiny fraction of a second after the Big Bang. And then there's gravity, standing apart, described by general relativity rather than quantum field theory, resisting unification with the other forces. Bringing gravity into the picture, creating a quantum theory of gravity, would be the final step, the completion of the unification program. And this is where things get subtle, where we reach the edge of what we know and venture into speculation and hope. The problem is that gravity is extraordinarily weak compared to the other forces. When you hold a piece of paper against a magnet, the electromagnetic force in that tiny magnet overcomes the gravitational pull of the entire Earth. Gravity only seems strong because it adds up over vast masses, because it's always attractive, never repulsive. So large objects like planets and stars accumulate enormous gravitational fields. But at the level of individual particles, gravity is negligible, too weak to measure in any particle physics experiment we can currently perform. This means that quantum effects of gravity only become important at incredibly small scales, scales much smaller than atoms, smaller even than the nucleus of an atom. This scale is called the Planck scale, and it's so small that we have no hope of probing it directly with experiments in the foreseeable future. At the Planck scale, quantum fluctuations in spacetime itself become significant. The smooth fabric of spacetime predicted by general relativity breaks down, and we need a quantum theory of gravity to understand what's happening. Several approaches have been proposed. The most famous is string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny vibrating strings of energy. Different vibrations of these strings correspond to different particles, like different notes on a violin string. In string theory, gravity emerges naturally, along with the other forces, from the way these strings vibrate and interact. It's an elegant idea, and it has many beautiful mathematical properties, but it's also extremely difficult to test experimentally because the strings are so small, far smaller than anything we can observe directly. Let yourself rest with this image for a moment if you like. Tiny strings, vibrating in multiple dimensions, creating all the particles and forces of the universe through their motion. It's almost musical, a cosmic symphony playing at scales too small to see, giving rise to everything from quarks to galaxies through the harmonies and resonances of these fundamental vibrations. String theory requires extra dimensions beyond the three of space and one of time that we experience. Different versions of the theory propose different numbers of extra dimensions, 10 or 11 in total, with the extra ones curled up so small that we don't notice them. This sounds strange, perhaps impossible, but mathematics allows it, and mathematics has often been a reliable guide to physical truth. Maxwell's equations predicted radio waves before anyone had observed them. General relativity predicted black holes and gravitational waves decades before they were detected. So perhaps string theory's extra dimensions and vibrating strings are real, waiting to be confirmed by some future experiment or observation. But string theory is not the only candidate for a theory of everything. There's also loop quantum gravity, which approaches the problem differently, trying to apply quantum mechanics directly to the geometry of spacetime, treating space and time themselves as quantized, made of discrete units rather than smooth continua. In this view, spacetime is woven from tiny loops, and the fabric of reality has a kind of granular structure at the smallest scales, like a finely woven fabric that appears smooth from a distance, but reveals individual threads when you look closely enough. And there are other approaches too, other ideas and frameworks, each with its own insights and challenges. The field is alive with creativity and debate, with physicists exploring different mathematical structures, different physical principles, trying to find the one that clicks into place, that explains everything we know and predicts new things we can test. You might notice a sense of vastness in all this, a feeling of how much we've learned and how much remains unknown. This is part of the beauty of the search for a theory of everything. It's not just about the endpoint, the final answer, but about the journey, the gradual unfolding of understanding, the way each generation builds on what came before, seeing a little farther, understanding a little more deeply. Let's wander now into cosmology, into the story of the universe itself, because a theory of everything would not just describe particles and forces in abstract terms, but would explain how the universe began, how it evolved, where it's going. And we do know quite a lot about this story, even without a final theory. The universe began, as far as we can tell, about 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space, but an explosion of space itself, a moment when space and time and energy all came into existence together, or at least began expanding from an initial state so hot and dense that our current theories break down. In the first tiny fractions of a second, the universe was unimaginably hot, filled with a soup of fundamental particles and radiation, expanding and cooling rapidly. As it cooled, forces that had been unified separated into distinct phenomena. First gravity, perhaps, then the strong force, then the electroweak force splitting into electromagnetism and the weak force. Quarks combined to form protons and neutrons. Electrons joined with nuclei to form the first atoms. Gravity pulled matter together into clumps that became stars and galaxies. Stars fused light elements into heavier ones, creating carbon and oxygen and iron, all the ingredients of planets and life. Stars died and scattered these elements into space, where they formed new stars and planets, including our Sun and Earth. And here we are, billions of years later, made of atoms forged in stars, trying to understand how it all works, trying to trace the chain of cause and effect back to the very beginning, to the moment when everything started. A theory of everything would tell us what happened in that first moment, what the initial conditions were, why the universe is the way it is rather than some other way. It would explain the values of the fundamental constants, the strengths of the forces, the masses of the particles, all the parameters that had to be just right for the universe to evolve in a way that allows stars and planets and life to exist. This question of fine-tuning, as it's called, is one of the deep mysteries. Many of the constants of nature seem to be precisely calibrated to allow complexity and life. If gravity was slightly stronger, stars would burn out too quickly. If it was slightly weaker, galaxies might not form. If the strong force were a bit different, atomic nuclei might not be stable. And so on, for many different parameters. Is this just coincidence? Is there some deeper principle that determines these values? Or are we living in one universe among many, a multiverse where different regions have different constants, and we happen to be in a region that allows our existence? String theory, interestingly, suggests something like a multiverse. It has an enormous number of possible solutions, different ways the extra dimensions could be curled up, each corresponding to a different set of physical laws, different constants, different particles and forces. This landscape of possibilities, as it's called, might mean that all these universes actually exist somewhere, somehow, and we're in one that happens to have the right properties for life. This is speculative, perhaps untestable, but it's the kind of question that a theory of everything raises, the kind of deep issue about existence and reality that we're forced to confront when we try to understand the most fundamental level. As you listen, you might feel the boundaries of thought becoming softer, the distinction between understanding and not understanding less important. That's the right way to approach these ideas. They're vast, and no one fully understands them, not even the physicists who work on them every day. What matters is the sense of wonder, the quiet awe at how much there is to know, how deep reality goes. Let's think about symmetry for a while, because it plays a central role in modern physics, in our understanding of forces and particles, and in the search for a theory of everything. Symmetry, in physics, means that something stays the same when you change your perspective in some way. A sphere, for instance, looks the same no matter how you rotate it. A pattern might look the same when you shift it to the left or right. These are simple geometric symmetries. But there are deeper, more abstract symmetries that govern the laws of physics. One of the most important is called gauge symmetry, which underlies all the fundamental forces. The electromagnetic force, for instance, has a gauge symmetry that's related to a mathematical structure called U1, which describes rotations in an abstract space. The strong force has a more complex symmetry called SU3. The electroweak force has SU, 2 times SU, 1. These might sound like meaningless abstractions, and in a sense they are just mathematical structures, but they determine everything about how the forces work, what particles they affect, how they interact. The Standard Model is built on these symmetries. The particles and forces aren't put in by hand, but emerge from requiring that the laws of physics respect certain symmetries. This is a profound idea. Symmetry is the foundation of physical law, as the reason why the universe has the structure it does. And in grand unified theories, these separate symmetries are combined into larger symmetries that unify the forces. In theories of everything, there might be an even larger symmetry that includes gravity, that encompasses all of physics in a single elegant structure. There's something almost mystical about this. The idea that the universe is governed by symmetry, by abstract mathematical patterns that exist independent of space and time and matter. Plato would have loved it, the notion that the world we see is a reflection of perfect forms, except now the forms are symmetry groups and gauge fields instead of ideal circles and triangles. And yet it works, this mathematical approach to nature. The equations make predictions, the predictions are tested, and they turn out to be right again and again to extraordinary precision. But symmetry also breaks, and this breaking is just as important as the symmetry itself. The electroweak symmetry, for instance, is broken in our current universe, which is why electromagnetism and the weak force appear different. The breaking happens through something called the Higgs mechanism, involving the Higgs field that permeates all of space, and the Higgs boson that was discovered at the Large Hadron Collider in 2012. The Higgs field has a non-zero value everywhere, even in empty space, and this breaks the electroweak symmetry, giving particles their masses. This is a subtle and beautiful idea. The universe has a kind of background field, invisible, intangible, but present everywhere, and particles acquire mass by interacting with this field. It's a bit like moving through syrup, which resists motion and makes you feel heavier. Different particles interact with the Higgs field with different strengths, which is why they have different masses. Electrons interact weakly, so they're light. The W and Z bosons that carry the weak force interact strongly, so they're heavy. Photons don't interact with the Higgs field at all, so they're massless, traveling at the speed of light. You don't need to hold on to these details to remember the mechanism or the particles. Just rest in the sense that there's a logic here, a reason why things are the way they are, even if the reason involves invisible fields and broken symmetries and abstract mathematical structures. The universe is comprehensible, at least in principle, even if the comprehension requires thinking in ways that seem far removed from everyday experience. Let's drift now into the question of what it would mean to have a theory of everything, what we would gain from it, what it would tell us. Some people imagine that such a theory would answer all questions, would explain every phenomenon, would make physics complete and finished. But that's not quite right. A theory of everything would be a theory of the fundamental level, the deepest laws, but it wouldn't necessarily tell us how to solve every problem in physics or predict every phenomenon. This is because of emergence, the idea we touched on earlier that higher-level phenomena can have their own patterns and principles that aren't easily derived from the fundamental laws. Chemistry emerges from physics, but chemists don't need to solve quantum field theory equations to understand chemical bonds. Biology emerges from chemistry, but biologists don't need to think about quarks and leptons to understand how cells work. Each level has its own appropriate description, its own effective theories, even though everything is ultimately grounded in the fundamental laws. So a theory of everything would not make other sciences obsolete. It would not answer questions about consciousness or love or art or why the stock market crashes. It would be a theory of the fundamental constituents and forces, of what the universe is made of at the deepest level, of how space-time and matter and energy are woven together. And that would be enough, more than enough, a completion of a quest that has occupied human minds for millennia. It would also perhaps answer some of the deepest questions we can ask. Why does the universe exist? Why these laws and not others? What happened before the Big Bang, if that question even makes sense? Is our universe unique, or one among many? What is the ultimate fate of the cosmos? A theory of everything might not answer all of these questions definitively, but it would constrain the possibilities, would tell us what kinds of answers are compatible with the fundamental structure of reality. And there's something profound in even attempting such a theory, in reaching for the most complete understanding possible, in trying to see the universe whole. It's an expression of something deep in human nature, the desire to understand, to make sense of existence, to find pattern and meaning in the chaos of experience. Whether we ever achieve a final theory or not, the search itself is valuable, the journey worthwhile. As you settle deeper into relaxation, perhaps towards sleep, let these thoughts become lighter, less defined, more like impressions than ideas. The theory of everything is not something you need to grasp or hold on to. It's just a direction, a pointing toward unity and simplicity, toward the hope that beneath all complexity there might be something elegant and true. Think about the universe as a vast tapestry, woven from countless threads. Each thread is a particle, a field, a quantum fluctuation, vibrating and interacting according to precise mathematical laws. From a distance, the tapestry shows patterns, galaxies and clusters, stars and planets, the structure of atoms and the flow of time. Up close, its individual threads, each following its own path, but constrained by the weave, by the relationship to all the other threads. A theory of everything would be like understanding the loom that weaves the tapestry, the underlying mechanism that determines how threads connect, what patterns emerge, why the whole thing holds together. We've learned a lot about the threads, about the patterns, but the loom itself remains mysterious, hidden behind layers of complexity and energy scales we can't yet probe. String theory imagines the loom as a vibrating multidimensional structure, where the threads are literally strings oscillating in hidden dimensions. Loop quantum gravity imagines it as a discrete network of quantum geometry, space and time woven from elementary loops. Other theories have other visions, other metaphors, other mathematical structures. And perhaps none of them are right. Perhaps the truth is something we haven't imagined yet, something that will require new concepts, new mathematics, new ways of thinking about reality. This uncertainty, this incompleteness, is part of what makes the search beautiful. We don't know the answer, but we can see the question clearly. We can see where our current theories break down, where they need to be extended or replaced. We can make educated guesses, explore possibilities, test ideas against what we do know, and slowly, step by step, we build understanding. We rule out paths that don't work. We find clues that point in promising directions. The Large Hadron Collider, that enormous machine buried under the border between France and Switzerland, smashing protons together at nearly the speed of light, is one way we search. It can't reach the energies where quantum gravity becomes important, but it can test the standard model, look for new particles, probe the structure of matter at the smallest scales we can access. The discovery of the Higgs boson was a triumph, confirming a prediction of the theory, showing that our understanding has some truth to it. But the collider has also found that the standard model keeps working, that there are no obvious new particles or forces at the energies it can reach. This is both reassuring and puzzling. Reassuring because it confirms what we know, puzzling because many physicists expected to find something new by now, some sign of physics beyond the standard model, some hint of the deeper structure. Perhaps the new physics is at even higher energies, beyond what we can reach. Perhaps it's subtle, requiring more data to see. Or perhaps nature has surprises we haven't anticipated, and there are other ways to search, other windows into the fundamental structure of reality. Astronomers observe the cosmos, looking for phenomena that might reveal new physics. Dark matter that we know is there from its gravitational effects, but can't see directly, dark energy that's causing the universe's expansion to accelerate. Gravitational waves from colliding black holes that let us test general relativity in extreme conditions. Cosmology and particle physics are converging, both trying to understand the same underlying reality from different perspectives. You might notice your thoughts becoming more diffuse, less linear, drifting between ideas like a leaf on a slow stream. This is the rhythm we want, gentle and wandering, no pressure to arrive anywhere or understand everything. Just the quiet presence of these ideas, these questions, these glimpses into the deepest structure of things. Let's think about time again, about what it means and where it comes from, because a theory of everything would need to explain time, to tell us whether it's fundamental or emergent, whether it flows or is just a dimension like space, whether the past and future exist in the same way as the present, or whether only the present is real. In general relativity, time is part of space-time, woven together with space into a four-dimensional fabric. There's no universal now, no absolute simultaneity. Different observers, moving at different speeds or in different gravitational fields, will disagree about what events are simultaneous, about how much time has passed. Time is relative, flexible, part of the dynamic structure of the universe rather than an absolute background against which things happen. In quantum mechanics, time plays a different role. It's a parameter, something external to the system, a backdrop against which the wave function evolves. This difference between time as part of space-time in relativity and time as an external parameter in quantum mechanics is one of the deep tensions between the two theories, one of the reasons they're hard to unify. In quantum gravity, whatever form it takes, time might be something else entirely. Some approaches suggest that time emerges from something more fundamental, that at the deepest level there is no time, only timeless quantum states, and that time as we experience it arises from the way these states are organized, from the flow of information, or the increase of entanglement, or the growth of complexity. This is speculative, perhaps strange, but it's the kind of radical rethinking that might be necessary to solve the deepest problems. Carlo Rovelli, a physicist working on loop quantum gravity, has written beautifully about time, about how it might be an illusion in some sense, a feature of our limited perspective rather than a fundamental aspect of reality. From the view of the universe as a whole, from a perspective outside spacetime, if such a thing makes sense, there might be no flow, no passage, just a vast structure, a space of possibilities, and we experience time because we're embedded in this structure, moving through it, observing it from within. These ideas are at the edge of what physics can currently address, where science blends into philosophy, where we're forced to think carefully about what our concepts mean, what we really know versus what we assume. And this is appropriate for a theory of everything, because such a theory would be about the deepest level, the foundation of everything, and at that level, our ordinary concepts might not apply in straightforward ways. You can let your mind rest on these thoughts, or let them pass by like clouds. Time, space, matter, energy, existence itself, all questions that physics touches but perhaps cannot fully answer, at least not in the way we might hope. A theory of everything would tell us the laws, the structure, but whether it would tell us why those laws and not others, why there's something rather than nothing, these remain open questions, perhaps always open, beyond the reach of empirical science. Let's return to the forces for a moment, to the way they shape the world at different scales. Gravity dominates at the largest scales, holding planets in orbit, binding galaxies together, curving spacetime around massive objects. Electromagnetism dominates at human scales, responsible for essentially all the phenomena of chemistry and biology, for light and color and texture, for the forces that hold matter together and keep you from falling through the floor. The strong force operates inside atomic nuclei, invisible to direct experience but essential for the stability of matter, for the existence of the periodic table, for the nuclear reactions that power stars. And the weak force, most subtle of all, governs certain radioactive decays, plays a crucial role in the sun's fusion reactions, transforms neutrons into protons, and vice versa in processes that seem obscure but are fundamental to how matter evolves and changes. Each force has its own character, its own mathematical description, its own particles that carry it. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and hypothetically gravitons for gravity, though gravitons have never been observed and might not be observable in principle. These force carriers are quantum particles, and their interactions with matter particles are described by quantum field theory, a framework that combines quantum mechanics with special relativity, that treats particles as excitations of underlying fields that permeate all of space. Quantum field theory is one of the great intellectual achievements of the 20th century, extraordinarily successful in predicting the results of particle physics experiments, in explaining phenomena from the behavior of electrons in metals to the decay of radioactive nuclei. But it has its limits. It doesn't include gravity. It has infinities that have to be carefully removed through a process called renormalization. And it doesn't answer the deeper questions about why these fields exist, why they have the properties they do, what the ultimate constituents of reality are. String theory proposes that the fields themselves are not fundamental but emergent, arising from the vibrations of strings. Loop quantum gravity proposes that space-time itself is granular, quantized, made of discrete units that give rise to the smooth geometry we observe at larger scales. These are different visions of what lies beneath the quantum field theory description, different attempts to go deeper, to find the truly fundamental level. And maybe the fundamental level is not particles, or strings, or loops, but something else entirely, something we haven't conceived of yet. Maybe it's information, patterns of bits or qubits. Reality is a kind of cosmic computation. Maybe it's a network of relations, nodes and edges in some abstract space, with particles and space-time emerging from the structure of the network. These are speculative ideas, explored in different corners of theoretical physics, and it's too soon to know which, if any, will bear fruit. But the diversity of approaches, the creativity of the search, is itself encouraging. It shows that we haven't given up, haven't decided the problem is unsolvable. We're still exploring, still imagining, still using mathematics and experiment to probe the deepest questions. And occasionally there are breakthroughs, moments when understanding leaps forward, when what seemed impossible becomes clear. The discovery that the universe is expanding was one such breakthrough. Edwin Hubble's observations in the 1920s showed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This meant that the universe is not static but dynamic, growing larger with time, which in turn meant that in the past it was smaller, denser, hotter, pointing toward a beginning, a moment of origin. This was unexpected, revolutionary, and it opened up cosmology as a scientific discipline, transformed our understanding of the universe's history and fate. The discovery of the cosmic microwave background radiation was another breakthrough. In the 1960s, Arno Penzias and Robert Wilson detected a faint glow of microwave radiation coming from all directions in the sky, uniform and cold, exactly what you'd expect from the afterglow of the Big Bang. Radiation that's been traveling through space for nearly 14 billion years, cooled by the expansion of the universe to just a few degrees above absolute zero. This was direct evidence for the Big Bang, confirmation that the universe really did have a hot, dense beginning. And more recently, the discovery of gravitational waves, ripples in space-time itself, detected by enormous laser interferometers that can measure distortions smaller than the width of an atomic nucleus. These waves were predicted by general relativity a century ago, but they're so weak, so hard to detect, that it took decades of effort to build instruments sensitive enough to see them. And now we can observe them from colliding black holes, from merging neutron stars, giving us a new way to explore the universe, a new window into extreme gravitational phenomena. Each of these discoveries, and many others, are pieces of the puzzle, clues about the nature of reality, constraints on what a theory of everything must explain. We know the universe is expanding and accelerating. We know dark matter exists and makes up most of the matter in the universe. We know neutrinos have mass. We know the Higgs boson exists. Each fact narrows the possibilities, tells us something about the underlying structure, guides the search for a deeper theory. Let yourself drift with this. The sense of progress, of gradual understanding, of knowledge building across generations. You don't need to remember the details, the names of particles or discoveries or theories. Just rest in the knowledge that people are working on this, thinking deeply, making progress, slowly piecing together the puzzle of existence. Now let's wander into the question of mathematics, its role in physics, the mysterious effectiveness of mathematical reasoning in describing the physical world. Why does mathematics work so well in physics? Why can we write equations that predict phenomena with extraordinary precision? Is mathematics something we invent, a tool we create to describe what we observe? Or is it something we discover, a language that nature speaks, existing independent of us? Eugene Wigner wrote about this, calling it the unreasonable effectiveness of mathematics, and it's a deep puzzle. We invent mathematical structures to solve particular problems, but then these same structures turn up in completely different contexts, describing phenomena we never imagined when we developed the mathematics. Group theory, invented to study symmetries of geometric objects, turned out to be essential for understanding quantum mechanics. Riemannian geometry, developed as pure mathematics in the 19th century, became the language of general relativity. Complex numbers, which seemed like abstract nonsense when first introduced, are fundamental to quantum mechanics. It's as if mathematics and physics are intertwined at the deepest level, as if the structure of reality is mathematical, as if the universe is in some sense made of mathematics. Max Tegmark has even proposed that the universe is mathematics, that physical reality and mathematical structure are identical, that what we call the physical world is just one mathematical structure among infinitely many that exist in an abstract Platonic realm. This is speculative, perhaps unprovable, but it captures something true about the relationship between mathematics and physics. When physicists search for a theory of everything, they're searching for the right mathematical structure, the set of equations or symmetries or geometrical objects that capture the essence of reality, and they trust that when they find the right mathematics, when the equations are beautiful and symmetrical and elegant, they've found something true about the world, not just a useful approximation but a deep description of what is. This trust in mathematical beauty has been justified many times in the history of physics. Maxwell's equations are beautiful, and they're right. Einstein's field equations of general relativity are beautiful, and they're right. The Standard Model Lagrangian, though complicated, has a beautiful symmetry structure, and it's right, at least within its domain of validity. So when physicists work on string theory or loop quantum gravity or other approaches to quantum gravity, they look for mathematical beauty, for structures that have elegance and simplicity and deep symmetry, trusting that these qualities are guides to truth. Of course, beauty alone isn't enough. The theory also has to make predictions that can be tested, has to agree with all the experimental evidence we've already gathered, has to explain things that previous theories couldn't. But in the absence of direct experimental access to the Planck scale, mathematical beauty and consistency are important criteria, ways of choosing among possibilities, of deciding which ideas are worth pursuing. You might feel the boundaries between waking and sleeping becoming blurred, thoughts becoming less distinct, more dreamlike. This is the space we're aiming for, where ideas float freely, where understanding is impressionistic rather than precise, where you can rest in the presence of these questions without needing to answer them. Let's think about infinity for a while, because it comes up often in physics, in mathematics, in cosmology, and it's connected to some of the deepest problems. When you try to combine quantum mechanics and general relativity, you often get infinite answers, predictions that certain quantities are infinite, which clearly can't be right. This suggests that the theories are incomplete, that they're breaking down at small scales or high energies, that we need a new framework that avoids these infinities. String theory avoids some of these infinities by replacing point particles with extended strings, smearing out the interactions over a small region instead of concentrating them at a point. Loop quantum gravity avoids them by quantizing spacetime itself, making it discrete at the smallest scales so that infinities can't arise. Other approaches have other methods, but the common theme is that infinities are a sign of trouble, a signal that we're pushing our theories beyond their valid range. But there are also infinities in cosmology, questions about whether the universe is infinite in space or time, whether it will last forever or eventually end. The current evidence suggests that the universe is spatially flat or nearly so, which might mean it's infinite in extent, stretching on forever in all directions. But we can only see a finite portion, the part from which light has had time to reach us since the Big Bang. Beyond that is the unobservable universe, which might be infinite or might curve back on itself, and we may never know for sure. And what about before the Big Bang? Did time have a beginning? Or is the Big Bang just a transition from some prior state? Some models of quantum cosmology suggest that time is finite in the past, that the Big Bang is the literal beginning of time, and it makes no sense to ask what came before. Other models suggest an eternal inflation, where our Big Bang is just one bubble in an infinite multiverse, constantly spawning new universes in an endless process that has no beginning or end. These questions touch on the limits of physics, on what can be observed and tested, on what science can answer, versus what remains in the realm of philosophy or speculation. A theory of everything might shed light on them, might tell us what's possible and what's not, but it might also leave some questions open, unanswerable in principle because they're outside the domain of empirical science, and that's okay. Science doesn't have to answer every question to be valuable. Understanding the fundamental laws, the structure of reality at the deepest level we can probe, is enough, more than enough. The rest is mystery, and mystery has its own beauty, its own place in human experience. Let's slow down even more now. Let the pace become almost a lull, words and thoughts drifting like snow falling in still air. We've covered a lot of ground, wandered through forces and particles, space-time and symmetry, cosmology and quantum mechanics, the search for unification and the dream of a theory of everything. And through it all there's been a common thread, a sense that beneath the diversity and complexity of the world there might be simplicity, unity, one fundamental structure from which everything emerges. This is a hope, not a certainty. We don't know if such a theory exists. We don't know if it's within reach of human understanding, if our minds and our mathematics are adequate to the task. But we keep searching, keep exploring, keep pushing the boundaries of knowledge, because that's what we do, what we've always done, since we first looked up at the stars and wondered what they were. And the search itself changes us, expands our perspective, makes us see the world differently. To know that you're made of atoms forged in stars, that the same laws govern your body in the galaxies, that space and time are woven together into a flexible fabric, that reality at its deepest level is quantum, probabilistic, strange. This knowledge changes how you relate to existence, gives you a sense of connection to the cosmos, a feeling of being part of something vast and ancient and ongoing. You are, in a very literal sense, the universe understanding itself. You're made of the same matter, governed by the same laws, evolved from the same initial conditions. And when you think about physics, about the structure of reality, you're participating in a process of cosmic self-awareness, the universe becoming conscious of its own nature through the minds of creatures like you. This might sound grandiose, but it's simply true. There's an unbroken chain from the Big Bang to you, a sequence of cause and effect, of particles interacting and combining, of stars forming and dying, of planets coalescing, of life emerging and evolving, of brains developing the capacity for abstract thought, for mathematics, for science. And here you are, the current endpoint of that chain, able to think about the beginning, able to wonder about the fundamental laws, able to search for a theory of everything. So even if we never find the final theory, even if it remains forever beyond our grasp, the search is meaningful, worthwhile, beautiful. It's an expression of what makes us human, this capacity for wonder and curiosity, this desire to understand, to see clearly, to know the truth about the world we inhabit. As you settle deeper now, perhaps very close to sleep, let all these thoughts become soft and distant, like lights seen through fog, present but not demanding attention. The theory of everything, the forces and particles, the mathematics and symmetry, all of it can fade into the background, leaving only a gentle sense of the vastness of what we're part of, the depth of reality, the ongoing search for understanding. The universe continues, stars continue to shine, particles continue to interact, space-time continues to curve and flex under the weight of matter and energy. And somewhere, physicists continue to work, writing equations, running experiments, thinking deeply about the nature of things. The search goes on, has always gone on, will continue as long as there are minds capable of curiosity and wonder. And you can rest now, knowing that the world is what it is, that it follows laws, that those laws can be understood, at least partially, at least enough to see the beautiful structure underlying everything. You don't need to understand it all, don't need to hold on to any of this. Just let it be there, a quiet presence, a backdrop to your drifting thoughts as you move towards sleep. The vibrating strings, if they exist, continue to vibrate. The loops of quantum geometry, if that's what space-time is made of, continue to weave their pattern. The fields permeate space. The particles dance their quantum dance. The forces hold atoms together and push galaxies apart. All of it continues, whether you think about it or not, whether anyone thinks about it or not, the vast mechanism of existence turning, evolving, creating the conditions for stars and planets and life and consciousness. And in this ongoing process, in this cosmic unfolding, there is room for rest, for letting go, for releasing the need to know or understand or grasp. The universe doesn't need your attention to exist. It simply is, and you are part of it, made of its matter, subject to its laws, briefly conscious, briefly aware, and that's enough, more than enough. So rest now, gently, easily, letting the theory of everything fade into a distant background hum, letting the forces and particles and fields and symmetries all blur together into a soft sense of the underlying unity of things, the deep structure that holds it all together, that makes the universe comprehensible, beautiful, worthy of wonder even as you release your grip on understanding and drift, finally, into sleep.